In this video, we're going to look at the forward pass of the transformer. And the transformer that we are looking at today is the decoder-only transformer. It's not the encoder-only transformer, right? Or it is neither the encoder-decoder transformer. So when we first hear the word a transformer, so we should know that there are three types of transformer. One is an encoder-decoder transformer, which basically has everything, an encoder and a decoder. Similarly, if we look at a decoder only transformer, it is going to only have the decoder stack, right? So this is only the decoder stack, this particular stack on the right hand side, right? So we are going to look at this particular transformer today. Along with that, we also have encoder only transformer. So the encoder only transformer is only going to have the encoder stack and not the decoder stack. The main difference between all of these three, or let's say, let me also tell you the use cases. So if you hear anytime encoder only transformer, think about a transformer like BERT, bidirectional encoder representation of transformers, right? Encoder only transformer are not generative in nature. They produce embeddings. The input is largely the same to all of these transformers. The input is large amount of text at training time also and at inference time also, right? But the use cases are completely different, right? So the encoder only transformer is bidirectional encoder representation of transformer, which is BERT, right? So you can look at or read the paper about BERT so that you understand what exactly it does. Produces embeddings, it produces contextual representation, it helps you use those embeddings for use cases. And for decoder only transformer, whenever you think about the GPT family, GPT-1, GPT-2, GPT-3, all of these are decoder only transformers, right? They are generative in nature. They are trying to do the next token prediction. The next token then completes a word, then it completes a sentence, and then it completes a story, right? So in an autoregressive way. So that is a decoder only transformer, right? So there also the input training time is large amount of text data, right? Assuming that it's not multimodal, it's only a text based transformer. And then comes the encoder decoder architecture. The encoder decoder transformer is also a transformer. The subcomponents more or less are same. It has an encoder stack and a decoder stack. The encoder stack produces some embeddings. Those embeddings become the source of the decoder's attention, which we also call as cross attention. And then the encoder decoder transformer produces something known as machine translation, language to language modeling, sequence to sequence modeling, English to French to English to German, whatever you want to do, right? So all of these three transformers are very much relevant in their own use case family, right? So today we are going to understand the forward pass of a decoder only transformer, which is the GPT family, right? So we will understand what happens at every process, right? So how does the forward pass happen? So this is, let's say, look at this particular portion. This is nothing but the inference time. So let's say let's just imagine that we are simply generating the next token. For this particular video, we will assume that one character is one token, right? It says that, the characters that we have written is 12. That means we have 12 tokens here, right? They're not subwords. Generally, if you look at the tick tokenizer algorithm, right? So the tick tokenizer algorithm is also available open source. So let's say we are using tick tokenizer algorithm and the GPT-4 tokenizer. It tokenizes the whole text into these many tokens, right? Where India hyphen is another token, India is another token, AI is another token, and hyphen SEM is another token. So right, so this is a subword. But what we are saying that keep H only as one token, E only as one token, L as a separate token. Every character in itself is a token, right? So if you look at here, just let's look at here. H is a token. H is represented as this particular vector in this particular dimension. So it's a 64 dimensional vector. The first 15 elements are these, right? Similarly, E itself is a token, L again is a token, O token, right? Space is a token, W is a token, R, O. All of these characters in itself are tokens. This is a very simple tokenizer algorithm that we used, right? So now let's say in an ideal world, if I am writing something like this, hello world, how are? It should predict something like you, right? So if you play on process, it should predict something like you. Now, the first phase is what happens to these tokens? And these tokens are now supposedly processed transformer. They act as the input, right? But not directly the tokens. The token embeddings will be the input, right, to the sublayer. If we look at the architecture of a decoder only transformer, let us observe carefully. This is the input, right? Now this input is going to go in this particular decoder stack. This decoder stack is first doing something which is known as attention, right? We're calling it multi-head attention. We are also calling it self-attention. Then there is also masking that goes on in the attention block, right? So largely, let's call it the attention sublayer, right? Then we are doing some residual, addition of residual, then we are normalizing it, then again it is going through the feed forward pass, or basically the feed forward linear layers. Then again we are adding some residual, right? So this plus means adding residual, adding input back to the output of the sublayer, adding input back to the output of sublayer, adding input back to the output of sublayer, then again some normalization, and then we are doing some text prediction, right? So this is the decoder stack, right? If you look at here also in the original paper, attention is all you need, this was the stack that was mentioned. So what it's saying is it's going to go feed embeddings, right? So these are the token embeddings. So it's written output embeddings because it's coming on the encoder, but assume that these are nothing but token embeddings because it's a decoder only transformer, right? So in the token embeddings, we are adding something which is known as positional embeddings, right? So after that, it goes to the attention sublayer, as we saw here, right? Now the attention sublayer obviously computes multiple heads, and it also does masking. That's why we call it masked multi-head attention, right? Now the input gets added to the output, which is nothing but adding the residual, right? So we add the residual, we normalize. That's why we call it add and norm, and we do it after every sublayer, right? Then let's say we again do multi-head attention, then we again add this particular residual and normalize, then we do feed forward pass, then we again do normalize, and then there we have one more linear layer, or let's say rather the output head, and then on top of it we have applied softmax distribution function to produce probabilities. From these probabilities we will be able to sample, from this probability distribution we will be able to sample the next token, right? And then keep it as our output. And if we do it in an autoregressive way during the predict phase, it will behave like a generative engine, right? And if we teach this particular transformer how to do conversations, right? So this natively does not know how to do conversations. This simply knows how to do next token prediction. We separately have to train another neural network on a lot of manually labeled conversations in order to teach this particular transformer the idea of conversations, right? So that's a totally different topic. But here, let's only understand how a decoder only transformer produces next tokens, right? So don't think of a decoder only transformer directly, as the chat GPT, right? In order to be able to chat from that, in order to make it that chatbot sort of AI, we need more additional steps in the post-training part, right? Here we are just looking at how do you produce a large language model, a transformer, a dense transformer, which is a decoder only transformer. Okay, awesome. Now, since we know that the input to the multi-headed attention block, or rather call it simply attention sublayer, right, is going to be embeddings. Which all embeddings? Token embeddings and positional embeddings, right? Now we learned that we produce embedding for every token. Every token is not represented as something like a number. Like h is not going to be represented as its character code, like maybe 1 2 3 whatever, or its ASCII code, right? H is going to be represented in a 64 dimensional vector, right? That is why we are calling h as an embedding vector. H will have its own embedding, e will have its own embedding. Similarly, every token is going to have its own embedding, right? Similarly, the position also is going to be represented in this higher dimensional space, which is 64 dimension, right? So assume that 64 dimension is the model dimension, right? Let's call it dk. So in attention formula we saw something known as dk, right? Let me just show you again in case you might have forgotten. So this, let's assume 64 as this dk, right? Now what we will do is we will combine, means we will linearly position wise add them, right? Position of h is also represented as a vector, e is also represented as a vector, l is also represented as a vector. And when we say that it is represented as a vector, we do not mean that we took another model which is, let's say, a token to vector model, word to vector model, character to vector model. to produce these embeddings. These embeddings are learnable weights, right? They are the main juice of the transformer. They are learnable weights. They are not static. They are not frozen. They will change with time, with during the training phase. At inference time, they'll obviously be fixed. They will not change inference time. But during the training phase, they will change with time, right? They will take their own shape. Now we take token embeddings to start with, right? And positional embeddings, the zeroth iteration, and then just combine them, right? So this is the start of the training phase. We combine all of these embeddings. Now we have a combined embedding vector. This has to be the input to the transformer, right? So right now, let's say these are 12 elements. We have 12 cross 64 dimensions, right? So this is not 15, it's 64. We have only represented the first 15 values, right? Now this has to go to the attention sublayer, right? Now it has come to the attention sublayer. What will attention sublayer do? Attention sublayer, we know, will produce something known as contextual representation. Whenever someone says attention, atten correlate attention with contextual representation, right? Now attention, if it's only happening in one block, especially in a decoder-only transformer, we call it self-attention. When you want to compute multiple such attention matrix, we call it multi-head attention, multi-head self-attention. When you want to do masking, causal masking, that means hide the future tokens, we call it masked multi-head self-attention. Right? So we'll keep on adding the prefixes. Right? We only started with attention, then we started calling it self-attention, then we started calling it multi-head attention, then we started calling it masked multi-head self-attention. Right? So all of these prefixes have their own meaning, right? So we have to understand that. We don't have to be scared of all of these complex prefixes. Okay, so why do we need multiple heads? We have discussed it in detail a lot of times. We need multiple heads. All of these heads are computed in parallel because we want to capture deeper hierarchical relationship in the language. Let's say one head is helping us capture the relationship in a language between a subject and a noun. Another head is helping us capture maybe the relationship between a noun and a verb, right? Then maybe noun and an adjective. To be able to understand the language better, only one head is not enough, right? One head makes a lot of sense, but one head is not enough. We need multiple heads of attention, gives us an idea that we understand the language better, that we understand the language in a more deeper and more hierarchical way, right? We're not only scratching the surface, right? So we compute all of these heads are will be computed parallelly. They're independent of each other, right? Head 0 does not need information from head 1, right? Otherwise also is true, head 1 does not need information from head 0. So all of these heads can be computed in parallel. All of these heads are simple matrices, right? So see, you can see that this particular head is also a matrix. Relationship, the contextual representation between H and H, E and H, L and E, and so on. We have masked all the future tokens. Masked means we have hidden all the future tokens. We have made them dead, right? Why? Because we don't want to see future. And I'm standing here, I don't want to see what's going to come next at training phase, right? This is the training phase, right? Why? Because during inference time, I will not know what is going to come after D. So I have to learn to be able to predict. So all of these heads have different informations, right? The same language in the same token size. Now what we need to do is simply need to concatenate all of them. Once we concatenate of them, we will produce something like a concatenated output, and that will go get multiplied with a projection matrix, which is WO, right? So we've seen that attention is a product of, or basically a scale dot product of Q, which is query, and key, right? So if you look at the formula here, right, attention is nothing but the dot product of query into key, and then again a division by model dimension. In our case it is 64, so 64 square root is going to be 8, and then we apply a softmax because we want to convert this raw score. This is a similarity score, similarity contextual representation score. We want to convert it into probability mass, and then we multiply it with the value matrix, right? All of these query, key, and value are matrices, right? So we talked about query, keys, and values, them being different matrices that explains the formula of attention, right? Now Q is being produced once we multiply once we multiply the input with WQ. Let me open one more link so that we can just revisit the idea of query, key, and value. We have explained it in greater detail in the last video where we discussed the paper attention is all you need. Now let's say Q is a matrix in itself, right? K is a matrix in itself, V is a matrix in itself. And how was it produced? It was produced by multiplying input X is input. What is input? The combined embedding matrix. It gets multiplied with another weight matrix known as WQ. This is also assumed and random in the start. This is also assumed and random in the start. This is also assumed and random in the start, right? X gets multiplied with WQ, X gets multiplied with WK, X gets multiplied with WP. Then we produce query, key, and value, right? So the idea of attention is the attention wants to know out of all the tokens, let's say I'm standing at SAT. SAT wants to know out of all the tokens in this token set, right? Or in my context window, which token should I attend to? And with what intensity, how do I relate to those tokens, right? So this is what attention is trying to produce, right? So query, key, and value are are simple matrices. They also are sort of embedding matrices. They are not exactly as embedding matrices, but they're being produced from those matrices, right? So what was the intuition behind query, key, and value? Query, the abstract idea behind query is, what am I looking for? What kind of patterns am I looking for in all my token set J, right? Key, the idea of key says, what do I have that other people are looking for? What patterns do I offer to other people, or basically to other tokens, not to other people, but to other tokens? Value, what content do I have, right? That will be useful, right? So we have to think about query, key, and value in an abstract term, especially with respect to databases. Databases is a very nice way to think about query, key, and value. Now assume that you understand query, key, and value, and you can build up attention, and you can capture multiple heads of attention. Now what is going to happen, right? Now we are going to pass it through the feed forward neural network, right? What is going to happen in a feed forward neural network? So after attention, every token passes through a two-layer neural network. So here we have two layers, right? It's going to get passed through this neural network. That means, so the feed-forward neural network architecture is completely the same. It is not any different. For someone who might not have seen feed-forward neural network, let me. So this is the architecture, right? You pass your input from this particular neural network after you come out of the attention block, right? And before you do this, you also have to add residual, right? So you adding residual means, let's say this is f of x, this is the produced output. You will again add embeddings, which was x plus f of x will happen. You will normalize. After you do x plus f of x and you normalize, then only you will pass all of these tokens through the feed forward neural network. So here the feed forward neural network has two layers, right? So input layer, which takes 64 dimensions, because every token or every embedding is represented as 64 dimensions. It has a linear activation function, it has a ReLU activation function, and it's going to expand or extrapolate it into 256 dimensions, right? So that means the next hidden layer is going to be in 256 dimensions, and then it is again going to project it to 64 dimensions, because we want to stay consistent with the model dimensions, right? Now what is going to happen after this? Again, we will go through something known as adding the residual and layer normalization, right? And then I think we completely done, right? Let's go through again the transformer blocks. Exactly happened. We had something input, had something as input, which were embeddings. Then after attention, we got output. Then we added the residual. In this case, the residual is nothing but x, right? Then again, we went through the feed forward network pass, or feed forward neural network pass, and we added again residual. So we did not discuss feed forward neural network in this particular video in greater detail, and neither we will in any of the transformer videos, because we will assume that you are already understand neural networks. They are the simplest multi-layer perceptrons feed forward neural networks, especially when you start learning deep learning. Okay, so now after this you're done, right? So just look at the residual. What naturally happens, you add x to your f of x, right? F of x is the output of the sublayer, x is the input to the sublayer. So you do input plus output, right? It really happens. This helps, this helps in the training times, and the gradients flow directly through the neural network. It preserves the information. This is a very important point. This preserves the information and keeps it more and more relevant, and the cascaded forgetting does not happen, right? It makes deep and deep networks easier to train, because the information preservation kinds of helps and adds the value. Okay, so each transformer block is going to do the same. So here we have four transformer blocks, right? Block 0, block 1, block 2, block 3. Each transformer block is going to have this phase, which is the input embedding, and the attention, then adding residual, then again doing feed forward network, then again adding residual, right? So after all of these four blocks, we will be able to pass the output through the softmax. The softmax is going to apply, softmax function on the 64 neurons that were part of the feed forward neural network, and every neuron will be assigned a probability, right? And the probability should sum up to 1, right? So this is the idea, right? So here we can say that we are simply having probabilities, right? So our model is not perfect, that's why we have something like random gibberish coming out, right? But if the model would have been perfect, it would have predicted hello world, comma, how are you, something like that, right? This is basically the feed forward pass of the neural the transformer of a dense transformer of a decoder only transformer. Now what we can actually see, what we can actually do is maybe implement it in the further upcoming videos and take it as a sample and mental model to understand all decoder only transformers, right? So I think we have discussed in greater detail every phase, and we are in one of the best stages to implement it in the further videos. Thank you for tuning in. I'll see you in the next video.